Before we get into parametric surfaces, we're going to remind ourselves of vector functions, which can be expressed as r of t is equal to x of ti plus y of tj plus z of tk, which can be expressed parametrically as x is x of t, y is y of t, and z is z of t. With t being a one-dimensional input, the output is actually a one-dimensional curve. That is, it occupies space, three-dimensional space, but the curve itself is only one dimension. That is, it's like a bent line. So this is the curve C given by r of t, and the parameter t maps to a point x, y, z in space, and strictly speaking, t doesn't appear in the graph, right? T is the input for the parametrically defined components x, y, and z, but t doesn't show up in the x, y, z R3 space. With that in mind, surfaces can be described as vector functions of two variables, and we write r of uv is equal to x of uvi plus y of uvj plus z of uvk. The parametric equations for the surface are x equals x of uv, y equals y of uv, and z equals z of uv. As with the parametrically defined curve, where t does not appear in the graph, u and v do not appear in the surface that is generated. Let's look at how we can parameterize something kind of basic. The plane that contains a point P naught, which corresponds to the vector r naught, which is given by x naught, y naught, and z naught, and vectors a given by a1, a2, a3, and b given by b1, b2, b3 can be expressed as a linear combination of a and b. R of uv equals r naught plus ua plus vb. So for any point P on the plane, we can find vectors that are a multiple of a, and so ua, and a multiple of b, and so vb, such that when I add those together, using the parallelogram law, I can achieve the desired point. This is kind of like saying that I and j span the xy plane. And r naught assures that the original point had been on the plane. But the point here is that this is parameterized as x equals x naught plus ua1 plus vb1, thinking about the components of a being a1, a2, a3, and b being b1, b2, b3. Likewise, y is y naught plus ua2 plus vb2, and z is z naught plus ua3 plus vb3. You'll note a parallel between the parametric equations of a line, which have only one input variable, and now here the parametric equations of a plane, which have two input variables, u and v. A sphere of constant radius, say a, and center 0, 0, 0, is parameterized as r is a function of phi and theta, a cosine of theta sine of phi I plus a sine of theta sine phi j plus a cosine of phi k. To ensure that we have the entire sphere, we'd say that phi goes from 0 to pi, and theta goes from 0 to 2 pi. You'll note the similarity to our conversion factors for going from rectangular to spherical coordinates. Instead of rho cosine theta sine phi for x, we have a fixed radius a cosine theta sine phi. And we need to have a fixed radius here because we aren't talking about 3 input variables here. We're only talking about 2. For a surface whose equation is given by a function, say z equals f of x, y, we use as the x parameter x and as the y parameter y. The z parameter, really exciting, f of xy. So the surface would be given by r of xy is equal to xi plus yj plus f of xyk. The parametric representation is easily adjusted in the event that we have, say, x as a function of y and z. It just affects which component is the one expressed using the function.